session. And before we start, I have several questions for you. The first one is, I prepare a practice exam. It includes 40 multiple choice questions to simulate our final exam. And the question is that, can you only study this practice exam? The answer is no. The answer is no. Because unfortunately, I cannot test you all the single concepts, definitions, just in this practice exam. But I'm 98% confident to say that I can test you almost all the topics in our final. But you know, after each topic, there are several definitions, concepts, so I cannot test you all of them. So that's why you still have to go over your notes or just go over my previous exam review packets. And also, my second question is that how many problems we have in the final? 40. Is that scary? 40? But good news, don't be panic. How long will our final exam be? 2 hours and 45 minutes. To be honest, that is the longest exam time I have ever heard. So probably all of you just spend 1 hour and a half minutes, then you are ready to go. So you have enough time, so don't be panic. And then, so how many of you print this and bring it to the, okay. And this time I will not post a solution manual, because you can, if you don't understand some part of this practice exam, you can still go to the YouTube, look it again and again. So I will not write a solution manual for you this time. Okay, so I think that's all the things I want to let you know. And again, just I want to let you know how I'm going to run this session. I will spend 1 hour and a half to finish this practice exam and leave approximately 20 to 30 minutes for asking questions. Okay? So, yes?
When you go to publish it on YouTube, can you leave timestamps of the solutions so we're not looking through the entire video for each solution?
No. No, I cannot do that. Okay, so are you ready to get some feeling about our final exam? Mm-hmm. Okay, let's start. First, in the exam, if the professor gives you this long problem, do you need to go over every word?
No.
Each word, just to read all the things? No, just look at the keyword. So look at our question, what is the population in the problem? What is the population? The population is a universe, is all the things. So in this problem, can you tell me what is our population here?
All U.S. high school students.
All U.S. high school students here. I need to change a pen. All U.S. high school students is our population. So here we choose B. By the way, what is our sample in this problem? 1,000 high school students. This is our sample. Good job. And then how about smoke at least once a day? What is that? It is a variable we are interested in focus on. So this is a variable. How about the percent of all high school students that smoke at least once a day? What is that? That is a statistical reference. The statistical reference is what? Is about the population based on the sample. So this is statistical reference. So far so good, the first problem. Easy peasy, right? And then the second one, what is the quantitative data? Age. How do you do that? Because quantitative data, you can use a number to count, right? Age maybe 18, 20, 12, 21. But gender is only male and female. Those are categories, right? How about race? Black, white, Asian, something here. Those are categories. How about country? United States, China, still category. So easy peasy, right? Then next one is a little bit interesting. If the distribution is skewed right, what is the relationship between the mean and the median? I will give you 3 graphs and let you to figure out what is a skewed right. First, second graph. This is bell curve symmetric. The third graph is like this. So what is the first one? Skewed left. How do you know that is skewed left? Because depends on the location of our tail area. If our tail area is on the left, then this is skewed left. How about this one? Symmetric, right? This one, skewed right, because our tail area is on the right side. Then, to figure out where is our mean and where is our median, we use a symmetric, the middle graph. So here, the mean is in the middle, median is also in the middle. This case, mean equals to median. How about skewed left?
The median is smaller than the mean.
Because the mean is easily affected by the tail area. So the mean is always closer to the tail area. That's why the mean is closer to the tail area and the median is not affected by the tail area. This is median. So in this case, can you tell me which one is bigger? Median is bigger. Can you see that clear? How about skewed right? The mean is closer to the tail area. The median is not affected by the tail area. So in this way, mean is bigger than the median. So what is our choice in this problem? Mean greater than the median, right? This is skewed right, mean greater than the median. Okay? So far so good? Then next one, I'm sure there will be a problem like this in our final. Because do you still remember in the exam 3, the professor gives us a problem. It is called what? Chebyshev rules, right? And he told us this problem will be in the exam 3, but high possibility in the final exam. And in the final review, he also gave us this problem. So how do we do that? The first identification, how do you figure out this is a Chebyshev rule problem? The first characteristic is that we don't know the shape of the distribution. We don't know the shape of the distribution because it didn't tell us at all. But what we only know is the average, which is mean, and also the standard deviation, sigma. Those two are what we only know. The average mu equals to 65. Standard deviation equals to 16. And the shape is our standard deviation equals to 2 sigma, right? Then what does the Chebyshev rule tell us? Within K standard deviation, we have the proportion is at least 1 subtract 1 divided by chi-square. How about above or less than k standard deviation is at most 1 divided by chi-square. So what is our k here? K is the number of the standard deviation, right? In this case, what is our k here? Our k equals to 2. And then, is that above k standard deviation or within the k standard deviation? This is above k standard deviation, right? Because we go to the right area. So which formula we should use? We should use the second one. Above or less than k standard deviation, our proportion is at most 1 divided by chi square. That is, in this case, is at most 1 divided by 2 square, which is equals to 1 over 4. We choose B, at most 0.25. So far, so good? B, yes? Oh, this is 2 sigma. Sorry about that, this is 2 sigma. Pay attention to your keyword. If you see the question asks you find the proportion within k standard deviation, you should use what? At least, right? If the question asks you above or less than k standard deviation, you should use at most. And our formula within k standard deviation is 1 subtract 1 divided by chi square. And at above or less than k standard deviation formula is 1 divided by chi square. Good? Okay, so let's move on. Then the problem 5. What is the keyword in this problem? The mount shape, right? If you see this keyword, what thing you want to use?
Empirical.
An empirical rule, right? Empirical rule. What does an empirical rule tells us? We have the mount shape, right? This is a bell curve mount shape. The mean is here. We have 1 standard deviation above the mean, which is mu plus sigma. 2 standard deviation above the mean, mu plus 2 sigma. 3 standard deviation above the mean, mu plus 3 sigma. The same thing below the mean, mu minus 1 sigma. Here, mu subtract 2 sigma. Here, mu subtract 3 sigma. And what is the proportion between mu and mu plus 1 sigma? It's 34%. The proportion, what is the proportion between mu plus 1 sigma and mu plus 2 sigma? This is 13.5%. What is this area between mu plus 2 sigma and mu plus 3 sigma? 2.35%. And then the tail area above 3 standard deviation is 0.15%. The same thing here, 34%, 13.5%. This one is 2.35%. This tail area below the 3 standard deviation is 0.15%. Okay? Then what is our mean here? The mean is 1230, right? And then the proportion we want to find is between 1110 and 1470. Where is 1470? It's above the mean, right? It's approximately here. 1470. Where is 1110? It's below the mean, approximately here. So then, what is the difference between those two numbers? The difference between those two numbers is equals to what?
Wait, are you talking about the numbers, like oh, no.
The difference between those two numbers equals to 240, right? Exactly equals to our 2 sigma. The difference between 1110 and 1230 is what? Is 120, exactly equal to 1 sigma, right? Then you know this number is at this point. This number is at 2 standard deviation above the mean. This is 1 standard deviation below the mean. Then the area you are interested in to find is this area. Okay? There are three components. First, 34% plus 34% plus 13.5%. This equals to approximately 81.5%. So far, so good? So my suggestion for you, you can draw this graph in your formula sheet. So
What's the last one? You said 0.15? Is it 0.15%?
yeah, this one,
Yeah.
0.15. Okay? Then the problem 6. The smallest value in the data is 1. The largest value is 100. What would be a reasonable guess for the standard deviation? So what is the keyword here? The guess, right? So if you want to use the guess to find the standard deviation, what formula you should use? Sigma approximately range divided by 4, or sigma approximately range divided by 6. What is the range in this problem?
The greatest value minus the smallest value.
The range equals to 100, the largest number, subtract the smallest number, 1, equals to 99. And we use 99 divided by 4, it is equals to what? 24.75, or 99 divided by 6 equals to what? 16.5. So we choose A here. So can you see that clear? Because I don't think this is clear enough. Is that any way you can just turn off those lights? Is that better, or? Huh? Sorry? So how to do that? So let's moving on. Just okay. So the number 7, we have 6 employees, 4 of which are males, 2 of which are 4 are males, and how many females? 2, right? And 2 are selected at random. What is the probability that both are male? So in order to select 2 employees, we have 2 steps, right? Select the first employee. After that, we select another employee. But in this case, we want the probability that both are males. So the first step, we choose the first male. The second step, choose the second male. What is the probability choose the first male?
4 and 6.
4 divided by 6. Because we have 4 males and we have 6 employees. And then we times the probability of choose the second male. In this case, what is our denominator?
3 and 5.
in this case, because we already choose one male, right? So how many male at rest? We have 3 males right now. And then what is the total number of our employees? 5, because we already choose 1. This equals to what? 4 over 10 equals to 0.4. So far, so good. Do you understand why use time between those two? We times those 2 probabilities. Because we have the process. In this process, we have 2 steps. In the first step, we have the first probability. In the second step, we have second probability. What we need to do is to time those 2 probabilities. So number 8. Patients arriving at hospital can select one of 3 stations for service. 2 patients arrived and each selected a station at random. What is the probability they selected the same station? How do you do that first? List the sample space. List the sample space. So let's say the first patient choose, we have 3 stations. Station A, B, and C. How about the first patient choose station A, the second patient choose station B? That is a possible sample point, right? Then how about AB? We finished. How about AC? The first patient choose A, the second patient choose C, station C. And then also we have BC. Here is a question. Is AB the same as BA? Is that right? Because let's say I choose the station A, you choose station B. Is that the same as I choose station B, you choose station A? That's a different thing, right? So the order does matter here. So which is BA is different from AB. So the same thing, CA is different from AC, CB is different from BC. Okay? And also, how about both of those patients choose A, station A, AA, and the same thing, we choose BB or CC. That is a total sample space. What did the question ask us? Select the same station. So our success here is AA, BB, and CC. We use our successes, 3 divided by the total number of sample points in the sample space, which is what? 9, equals to 1 over 3, which is C here. So far, so good? Good. So then this one, oh yeah, just here is only one arrow is here, because here we change the choice D to 0.25. S represents a sample space. A, we have 2 numbers, 0.1, 0.4. B, we have 2 numbers, 0.1, 0.2. What is the probability of A? What does AC means? A complement. A complement. So AC, what is the probability of AC intersection event B? So here, how do you represent A complement? Our A is 0.1 and 0.4. Then what is A complement? Is all other elements in the sample space except the elements in the event A. So which is, we don't use 0.1 because it already exists in the event A. We don't use 0.4, but we use 0.2 and 0.3. 0.2 and 0.3. So far, so good? That is how we find the complement. Then what is event B? B is 0.1, 0.2. The problem tells us we want to find A complement intersection B equals to what? Intersection means the common things between those 2 sets. the common things. What is a common thing here? 0.2, right? And then we want to find the probability of AC intersection B equals to, we only have this success, which is our denominator is 1, denominator is our the elements in the sample space, which is we have 4 elements in the sample space, which is 1/4 equals to 0.25. We choose D. So far, so good. If you have any questions, you can ask me now or later. So don't wait until your final exam, okay? Then, next one. Colas A, B, C. 2 people taste them and pick their favorite. Suppose each picks at random. Probability at least one picks A or neither picks C. How do you do that first? What is your first step?
Sample space.
Of course, sample space. But there is another thing you need to do. It's more important. Set up events. Set up events. We use event A to represent at least one picks A. We use event B to represent neither picks C. Okay? And then the question asks us the probability at least one picks A or neither picks C. So what is the keyword here? Or. How do you represent that? By using the mathematical symbol. That is a union, right? If you see or, which means you should use a union. The question asks us A, the probability of A union B. Okay? Right now, you can list your sample space. Here, the first person choose A, the second person choose B. Also, AC and BC. So does the order matter here? I mean, are the AB and BA the same thing? No, because if I choose A, you choose B is different from I choose B, you choose A, right? So the order does not matter here. BA, CA, CB, right? How about they choose the same thing, like AA, BB, CC. Those are total sample points in our sample space. Okay? And then what is our event A? At least one picks A. So how about AB? Is that satisfied this? AB is satisfied because we have one A here. How about AC? The same thing. BC, there is no A. But our event A is at least one A there. So BC does not satisfy it. BA satisfy, CA satisfy, CB does not satisfy. There is no A inside. AA, of course, satisfy. That's all the things. How about our B, event B? Event B is neither picks C. And that means there is no C, right? So if that AB satisfy, right, there is no C inside. And AC does not satisfy. BC does not satisfy. And BA, CA does not satisfy. CB the same. AA, there is no C. BB. That is all the sample points in event B. Right now, the question asks us find the A union B, which is what? The common things, the common sample points. So AB, AB, the common things. How about BA? BA here, the same thing. AA, the common thing. BB, only event B has BB, but event A does not have BB. That is not a common thing, so we don't list here. So AU, oh, sorry about that. It's wrong, it's wrong. I mean, the the probability A union B equals to the probability A plus probability B minus P A intersection B. Right now, I want to find A intersection B. Because right now we are talking about the common things, right? That is intersection. A intersection B, we have 3 elements there. And then what is the probability of A here? We have how many sample points? 1, 2, 3, 4, 5. 5 divided by our sample space. We have 9 elements in our sample space. Plus the B, probability of B, 4 elements divided by our sample space. Subtract the probability of A intersection B, 3 elements divided by our sample space. Do you know why I represent the probability A union B equals to probability A plus probability B subtract probability A intersection B? What is that? Just a second. That is additive rule. If you find the probability of those 2 events, their intersection, their union, so you have to use additive rule, which is remember, you have to subtract the probability of their intersection at the very end here. Yes, do you have questions? Okay. So we get 6 over 9 equals to 2 over 3. We choose B here. So far, so good? Then the next problem. This is a table problem. So look at what is the probability selecting a student in the upper division given the student is under 20 years of age. What is a keyword here? Given. So that is a conditional probability, right? Condition here is the student is under 20 years of age. The keyword is here, given. Still, we set up events first. Our event A is student in the upper division. Event B is what? Is our condition under 20 years old. What does the problem ask us? Which is the probability of A given B, right? This equals to our conditional formula is probability A intersection B divided by the probability of B. Okay? So then your next step is to find the probability of A intersection B. How do you do that? Looking at the table. A intersection B, which is under 20 and also in the upper division. So what is their intersection? 9,600. This is probability, so we have to use our successes, 9,600 divided by the total number of students, which is 60,000. Because this is our total number of students. What is the probability of B? The event B is under 20 years old. Under 20 years old, we have 24,000 students. This is our successes divided by the total number of students, 60,000, equals to 9,600 divided by 24,000 equals to 0.4. We choose A here. So far, so good? Good? Let's move on. The problem 12. Cola ABC, 2 people taste them and pick their favorite. Suppose each picks at random. What is the probability at least one picks A, given that neither picks C? Actually, this is the same problem as the problem 10 before, right? We have 3 colas. But the difference from the problem 10 is here our keyword changed to given. So right now we have a conditional probability problem. Sorry? Okay. Then, do you still know our event A is at least one picks A. Event B is neither picks C. And then, what is our conditional probability here? Probability of A given probability of B. Right? Equals to probability A intersection B divided by the probability of B. What is the probability of A intersection B? We already found here. 3 successes divided by the total sample space, which is 3 divided by 9. What is the probability of B? B, we have 4 successes here, event B. 4 divided by the sample space, 9. Equals to 3 divided by 4, which is, we choose the D is right. So far, so good. We just changed the keyword. The previous one, the keyword is or. This one, the keyword is given. Okay? So then next one is very easy. The probability A, 0.2, probability of B, 0.5. If A and B are independent, what is the probability A intersection B? How do you do that? Shout it out. A times B. So the probability of A intersection B equals to probability of A times probability of B equals to 0.2 times 0.5 equals to 0.1. Choose C. Because if those two events are independent, then we can times them directly. Next one, counting rules. Counting rules. First, try to figure out what rule you should use in the problem 14. We want to build a car, and then this car can either standard or automatic. 2 choice here. In one of 8 colors, 8 choices here. And in one of 3 body type, 3 choice here. We want to build a car, and what we need to do, how many steps we need to do to finish this process. We have 3 steps. Step 1, we choose standard or automatic, right? 2 possible ways to finish. Step 2, we choose color. We have totally 8 colors, right? 8 possible ways to finish this process, to finish this step. And then the third step, how many ways we have to finish this step? 3 body types. Then how do we do with those 3 numbers? Times them, then we got 48. This is the total number of different cars. This is a multiplicative counting rule. And this is also the easiest one for you to forget in the exam, because most of you only memorize the permutation and combination, but forget the easiest counting rule here. Okay? Because here you have the process, and you have several steps to finish this process. And what you need to do is to times all the possible ways in each step. The second one, we have 12 UCF students. How many ways can I choose 6 of students to participate in a special project?
26.
Does the order matter here? Do you arrange them? No, you just choose, right? We choose 6 from 12. That is combination, because order does not matter here. We just choose. That equals to what? 924. So does anyone know how to use calculator to calculate permutation and combination? This is important. It can save you time in the exam. Do you know how to do that? So because everyone's calculator is different, this is mine. Do you see here, this is this button, above this button, there is NCR, C, which means what? Combination, right? The first letter, combination. And here is NPR. NPR means what? Permutation. Usually, if I want to do here, we choose 6 from 12. We usually press the largest number first, 12, and then shift, combination C, choose 6. Choose 6 from 12 equals to 924. Okay? Good. So let's move on. The problem 16. We have 36 golfers. And how many ways they can place first, second, and third? So does the order matter here? Yes. First, second, third. Of course, the order does matter here. So what rule you want to use? Permutation, right? We choose 3 from 36 and then arrange them. How do we use a calculator? 36, shift, permutation, choose 3 equals to this number. We choose D. Easy, right? You just take several seconds to finish this problem. Good? Then next one, we have a table here. And it asks us what is the expected value of x. How do you do that? We have the formula to find the expected value. EX means expected value equals to sum of x times px. How do you apply this formula? What is our first value of x? 1 times corresponding probability, 0.02. Then sum plus the second value of x, 2 times corresponding probability. The same thing, 3 times 0.43 plus 4 times 0.14 plus 5 times 0.11. This equals to 3.02. We choose A here. The things you may do wrong is that you have to time first, then do the sum. Time first, then do the sum. Okay? Good? So then, next question is really easy. It's really interesting because some students just guess in the exam and how many problems he can get right. Let's say 5 questions, multiple choice quiz. In this quiz, we have 5 problems. And each question has 5 choices. Suppose a student guesses, does not know anything, just guess. What is the probability of getting at least 1 correct? First, identification. What is the type of this problem? We use variable x to represent the number of problems guessed. Is that guessed? Correct. Then what is the possible value of x? Maybe 0, right? He got 0 right. Maybe 1, only get 1 right. Maybe 2, maybe 3, maybe 4, maybe 5. right? That is all the possible values of x. Then is x discrete or continuous? Is that countable? Discrete, right? Then go to our discrete family. How many family members in our discrete family? 3. The first one, binomial. Second, Poisson. Third, hypergeometric. If the professor wants to test you something about Poisson distribution, he will tell you in the problem, this is a Poisson distribution. But here, there is no Poisson in this word, right? So you just choose from binomial or hypergeometric. How do you identify that? Look at that. We have 5 questions, and each question has 5 multiple choice. Then we have how many trials here? 5 trials. Is that right? Trials. We have 5 problems, 5 questions. Each question we have 5 multiple choice. Are those problems identical with each other? Because each problem we have 5 multiple choice, right? Are they the same with each other? The problem 1 we have 5 choice. The second one we are doing the same thing, 5 choice. So those trials are identical with each other, right? Identical. And are they independent with each other? Yes. Which means the performance of this student doing correct in the problem 1, does that affect his performance in the problem 2? No, right? So that's why those trials are independent with each other. And then what else? So what is the probability? How many outcomes we have? We have 2 outcomes, which is guessing correct and guessing wrong. Right or wrong? And then what is the probability of guessing right? Equals to, because we have 5 multiple choice, only 1 choice is right. So the probability of guessing right is 1 divided by what? 1 divided by 5, right? The probability of wrong is 4 divided by 5, because there are 4 wrong choices. Then here, can you identify whether this is binomial or hypergeometric? This is binomial because it satisfies all the characteristics of binomial. Then the question asks us getting at least 1 correct. X bigger or equal to 1. If you do this way, what do you need to do? You need to x equals to 1 plus probability x equals to 2 plus dot 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 until the x equals to 5, right? So how many times you have to use the binomial formula in this case? 5 times, right? 1, 2, 3, 4, 5. That's lots of calculations. Is there another way you can use to save your time? How about thinking oppositely? Just the probability of x bigger than or equal to 1. I can use 1 subtract the probability of x less than 1. Then the probability of x less than 1 equals to probability x equal to 0. Right now, in this case, you only need to do 1 calculation to apply the binomial formula. Okay? So this equals to 1 subtract. We choose 0 from 5 as our correct problem. The probability of our correct problem, guessing correct, is 1 over 5. The power is 0. The probability of guessing wrong is 4 over 5. The power is 5. Use 1 subtract this one, this thing. So our answer is 0.672. We choose A here. This part just apply the binomial formula. Yes?
Question. So it's 1 minus
You mean this number?
Yes.
That's zero.
0.
Because in this case, when x equal to 0 means the student gets 0 correct question. There is no right problem, no right guess, right? Then the next problem, the same situation, but ask you how many problems would you expect this student getting correct? What is the keyword here? Expect, which is expected value. In the binomial, expected value equals to the mean equals to n times p. N is the number of trials. In our case, n equals to 5 because we have 5 trials. P is a probability of success, which is a probability of guessing correct. It's 1 divided by 5 equals to 1. So our conclusion is that if the student only guess to do this quiz, so how many problems do you expect him to be right? Only 1. Because our expected value is 1, we choose A here. Yes? Sorry? Because right now it's x equal to 0, right? Which means there is no correct guess. So 5 choose 0, we choose 0 as our correct guess. Then our probability of correct guess is 1 over 5. The power is 0.
So how do we set it to 5 choose 0 in our calculator?
Because right now we only choose a number of correct guess. Okay? In this case, our x equal to 0, so which means our correct guess is 0. That's why we choose 0 here. Okay? Good. Okay, then next one. The keyword Poisson distribution with a mean of 9 births per day. So this is a Poisson problem, and the mean is 9. So we use mu equals to lambda equals to 9. Lambda is a component in the Poisson formula. We use x to represent the number of births on a given day. The probability of x equals to exactly 6 births. So the probability x equal to 6 equals to, we apply the Poisson formula. The Poisson formula is equals to lambda x e negative lambda x factorial. We plug x equal to 6 and lambda equals to 9 to this formula. Then we get lambda is 9, x power is 6, e negative 9 divided by 6 factorial. This one equals to 0.091. We choose B in this problem. So first, this is our mean. And also this is value of the lambda equals to 9. And our x equals to 6. Plug in the formula, lambda equals to 9, x equal to 6. Then you get your probability. Okay? Then next one, think about that. What we already go over, the binomial and the Poisson. There is another family member in the discrete family. What is that? Hypergeometric. So next problem, we have 10 DVD players. 3 are defective, 5 are selected for inspection. What are the probabilities of that 2 of them are defective. In the hypergeometric, how do you identify that? We always have 2 categories. Like this one, the first category is non-defective. The second category is defective. So let's say here, we have DVD. 2 categories. First, defective, non-defective. We have total 10 DVDs, right? So the problem tells us 3 are defective, so that means 7 are non-defective. Then we choose how many? We choose 5 for the inspection. The problem asks us, what is the probability that 2 of them are defective? So in this category is 2. Then what is in the non-defective category? 2 plus what equal to 5? 3, right? Then in order to do that, our probability for this problem is we choose 2 from 3 in the defective category, and choose 3 from 7 in the non-defective category, divided by the total possible ways can be chosen, which is 10 choose 5. Because we choose 5 DVD for inspection out of 10.
Is that a combination? Would it be like 3 C?
Yes, if you use a combination, that is choose 2 from 3 times choose 3 from 7, then the denominator is choose 5 from 10. And then this equals to 0.42. We choose D in this problem. Or other situations like the die or not die, those 2 categories. The relationship between those 2 categories are opposite with each other. So defective, non-defective, opposite. Die, not die, defective, opposite. Okay, good. So then we go to our continuous family. The depth of the river is uniform, keyword uniform, from -2 to +2. What is the probability that change is greater than 1 absolute value? So draw the graph. The shape of the uniform distribution is an horizontal line, right? The range of this distribution is -2 to +2. This is a mean of the uniform distribution. The problem asks us, find the probability the change is greater than 1 absolute value. Where is 1 absolute value? It's 1. Also, it's -1. Greater than 1 absolute value, this is area we want to find, also includes this area. So the shaded area is what we are interested in to find. How do you represent those 2 areas? So first, we have to find the head, right? Head of the distribution equals to 1 divided by 2 subtract -2, which is, you say the total area under the curve is 1, and then divided by the length here. 2 subtract -2 equals to 1 divided by 4. This is our head. And then what is area here? It's equals to 1 divided by 4 times the length here equals to 1. The same thing here. 1 divided by 4 times 1 equals to 2 divided by 4 equals to 1 divided by 2. We choose D in this problem. So far, so good? Yes? What? This one? Oh, 1/4. What is then? Are you ready for the next one? The next one, what is a z-value for the 95th percentile? What does a percentile mean? Z-value is a standard normal distribution, right? Percentile is a number, and below this number, the area is how many? Like in this case, is 35%. So below, where is that number? It should be below the mean because this area is 35%. We want to find this z-value. How do you find the z-value? By using the z-table, right? You have the tail area 0.35. Then you can find this area, which is you use 0.5 to subtract 0.35 equals to 0.15. Because the reason why we want to find this area is because the z-table only reads this area. We should go to the z-table 0.15 and find the corresponding z-value is 0.93, but because this z-value is less than the mean, which is -1, negative 0.39, we choose B in this problem. Do you know how to use the z-table, by the way? Because here we have to use the area is 0.15. And look at the 0.15, the area in your z-table. Point 15. Here, where is 0.15? It is between those two numbers. 0.15 is between those two numbers, right? And then, right now, which number you should use? Use a number closer to the 0.15, which is this number. 0.1517 is closer to the 0.15. Then your corresponding z-value is 0.39. That is why this is 0.39. But this z-value is below the mean, which is negative. Then you add the negative sign before it. This is negative 0.39. Good? Okay, so let's moving on. Next one. X is a normal variable with mean 600 and sigma 100. Find the probability of X between 360 and 710. So we draw the normal curve. This is Z. Oh, this is first we use X. The mean of this distribution is what? 600, right? And then we want to find the probability of X between 360 and 710. So 360 is approximately here. 710 is approximately here. We want to find this area. Is that enough for you by only using the value of X to find the corresponding area? No, because you have to use the z-value from the z-table. So our z value, how about the corresponding z value of 710? How do you do that? You have to do the standardizing, right? Transform from x to z score. How do you do that? Z equals to x subtract mu divided by sigma. Right now it's 710 subtract mu 600 divided by sigma. What is our sigma here? 100, which is 1.1. The corresponding z value is 1.1. The corresponding z value of 710 is 1.1. How about here? The z value for 360. We do the same thing. Z equals to x minus mu divided by sigma equals to x 360 minus 600 divided by 100 equals to what? Negative what? That is negative 1.2. Negative 2.4. So the corresponding z value here is negative 2.4. Then you have those z values. Then you can find this part, this area, and this area individually by using the z table. This area equals to 0.3643. This area equals to 0.4918. Then you add those two areas. We get the 0.88561. Yes? Sorry?
So you took the 2.4, which is the table, found the value of area. That's it.
Yeah, if 2.4, the z table find the area between this number and this number. This is what the z table find. And also your corresponding z value is 1.1. This area is what your z table find. Okay, then next one, lifetime of an electronic component has an exponential distribution with mean 100 hours. Find the probability that components operates at last less than 100 hours. So this is another family number in our continuous family, which is exponential distribution. The exponential distribution is like this. And what do we want to find? Less than 100. This is 100. We want to find this area. Okay? So what is the formula of our exponential distribution? Which is x larger than equal to a, probability of x larger than equal to a equals to e negative a divided by theta. So what is our a here? In this problem, what we want to find is the probability of x less than 100. So do you see the difference here? The formula gives us bigger or equal to, but here what we are going to find is less than. How do we transform that? Use 1 subtract, right? Use 1 subtract the opposite, x bigger than equal to 100. Then we get the same format of our formula. Okay? Then plug in 1 subtract e negative here, the value of a is 100. Divided by theta. What is theta here? Theta equals to mu equals to 100. This is the formula of the exponential. Theta equals to mean, which is mu, equals to 100. Plug in 100 here. This equals to 0.63. We choose we choose C in this problem. Okay? Then let's move on. The next one, this is about unbiased estimator. X bar is unbiased estimator of mu. What is the mean of the sample distribution of X bar? So what is the definition of the unbiased estimator? Statistic T is an unbiased estimator of parameter theta. Then we can get the mu of T, which is the mean of the sample distribution of T, equals to theta. Yes?
How about that? How would you type in the 1 minus b negative 100 over 100 into your calculator to get the answer?
You mean this one?
Yeah, how would you put that in your calculator?
Can you ask me later? Because this is a simple question. Okay, just ask me later. Okay. So let's keep going here. If the statistic T is an unbiased estimator of parameter theta, then we have the mean of sample distribution of T equals to theta. How about we plug, right now, what is our T in this situation? Statistic is X bar, right? We change the T to the X bar. And then what is the parameter in this case? Which is mu. Then we plug in here the mean, which is mu of T. T is our X bar, equals to theta. Right now in our case is mu. Then we get this, which is the mean of the sample distribution of X bar equals to mu. So then the question asks, what is the mean of the sample distribution of X bar? We choose mu, which is B. So far, so good? Okay, then next one. We have two unbiased estimators. The variance of A is 2 and the variance of B is 1. What we should use to estimate mu? Right now we have two unbiased estimators. We want to choose the best one. What concept you should use here? Which is minimum variance, right? If we have two unbiased estimators and you want to choose the best one, how do you compare them? You should choose the one with the smaller variance. Choose the one with a smaller variance. Here, A and B, the variance of A is 2, the variance of B is 1. Which one is smaller? Which is the unbiased estimator B has a smaller variance. That's why you should choose unbiased estimator B. So what is the value of our B? Is 21. B is our answer here. Okay? So far, so good? So the average age in an elder community is 65 years old with standard deviation of 16. We sample 64 residents. Find the probability that their average age is less than 60. Yes. Oh, sorry about that. So what is our keyword here? The average, right? The average, which means we are dealing with sample distribution, not X. Right now we are dealing with X bar. This is sample distribution problem. So here we have normal curve. This is the distribution of the X bar, which is the sample distribution. what is the mean of the sample distribution? Which is mu x bar equals to what? Equals to the mean of the population, equals to mu. How about the standard deviation of the sample distribution? Is that sigma? Right? That is sigma divided by square root of n. Okay? So do remember to apply those equations when you are dealing with sample distribution. Okay? So what is our population mean? The average age with standard deviation of 16, and the average age is 65, equals to 65. This one equals to 16 divided by root square of 64. The number, the n is our sample size, 64, equals to 2. Okay? Then go back to our problem. Find the probability that average age is less than 60. Is less than 60. Where this is the mean of the sample distribution is 65. Where is 60? Below the mean. Here. And then the area we want to find is less than 60. This is the area we want to find. Okay? The same thing. If you only have the value of x bar, are you able to find the area and the curve? No. So what value you should use? You should use a z value by using the z table to find the area and the curve. So here, corresponding z value. What is the corresponding z value of 60? Z equals to x bar subtract mu divided by sigma x bar. What is x bar here? This point is 60. Subtract mu is 65 divided by sigma x bar, which is 2, equals to what? Negative 2.5. This corresponding z value is negative 2.5. Then we have our z value, negative 2.5 here. Using the z table, find this area is 0.4938. So then the area we are trying to find is 0.5. Use a half of the graph. Subtract the area is read from the z table, 0.4938 equals to 0.0062. We choose A as our answer. Yes? 2? Oh, yeah, this is a standard deviation of the sample distribution. We use the standard deviation of the population divided by root square of the sample size. Sigma equals 16, n equals 64. Okay? Good. Okay, finally, we go to our exam 4 stuff. So far, so good? From exam 1 to exam 3. Right now, we are going to build confidence interval and do the test of hypothesis. Okay? Then, right now, we have the sample 40 women has a mean 76.3 and standard deviation 12.5. We want to construct 99% confidence interval for mu. So what is the parameter we are dealing with here? P or mu? Mu. Are we going to do the test of hypothesis or build a confidence interval? Build a confidence interval, right? Then here, do we have a large sample size or small sample size? Large, because our sample size is 40, greater than or equal to 30. Okay? We have a large sample. Okay? And we are doing find confidence interval for mu. So I think I have prepared some good thing for you. Here, this one. Right now we are dealing with mu, and we have large sample size. Then we want to build a confidence interval. Then this formula is what we are going to use. It's very convenient for you to identify which formula to use, right? So if you want, you can copy this chart in your formula sheet. And then the formula we want to use is x bar plus minus a alpha divided by 2 times sigma divided by root square of n. What is our x bar here? The mean of 76.3 plus minus z alpha divided by 2. Do you still remember in the exam 4 review I gave you a gift? Okay. So this one, if you want to use, you don't have to calculate repeatedly, because you see, right now we want to build a 99% confidence interval. Then the z value is 2.575. You don't have to use a z table and calculate it again. You can write this down in your formula sheet. Write it really small. Okay. Then our z value is 2.575 times, what is sigma here? 12.5 divided by root square of n, sample size equals to 40. Then we get our answer in this problem is 71.121 to 81.39. We choose C as our answer. So far, so good? Okay, so then the next thing is how can we decrease the width of the confidence interval? We have 4 choices here. Decreasing the x bar. Does that work? This is a formula of our confidence interval. We decrease the value of the x bar. Can we decrease the width of the confidence interval? No, because if we do decrease the value of the x bar, which means we just move the confidence interval horizontally. We didn't change the width. We just move horizontally. So the first one does not work. How about decreasing the confidence level? So let's say right now we have a 99% confidence interval. So what is the middle area? 0.99, right? Our confidence level here is 99%, which is this is our confidence interval, lower bound, upper bound. The middle area is 0.99. And then I decrease our confidence level to 90%. Then we get our new confidence interval, which is the area between the lower bound and upper bound of the confidence interval is 0.990. So what happened to our confidence interval? Shrink, right? So the width of the confidence interval decrease. That is what we ask. We choose B. Okay? And then the choice C, decreasing the sigma, do we have the power to change the value of the sigma? We don't have that. We cannot do that because the sigma belongs to the population, and we have no control of that. Decreasing the sample size. Decreasing the sample size, which is we're decreasing the value of n. Then the denominator decreases. What happened to our sampling error? Denominator decreases. What happened to our sampling error? Increases. And then x bar plus minus a bigger number, which makes the width of our new confidence interval becomes larger. Right? Because our sampling error becomes larger. then the width of our confidence interval becomes larger. So estimating the average salary of accountants, we want to estimator be within here with 92% confidence, knowing that salary range is from this to this. Find the sample size n. Okay, go back to our chart. What are we doing here? Do we build in the confidence interval?
No.
Are we doing the test of hypothesis? No. So we are finding the sample size. Finding the sample size, go to the chart here. We are dealing with, here, the parameter we are dealing with is an average, right? Which is mu. The parameter is mu. We go this part, and then find the sample size, use this formula. N equals to this part. So the formula we are going to use equals to n z alpha divided by 2 square 8 sigma square SE square. Okay? First part, what is z alpha divided by 2? Z alpha divided by 2 depends on our confidence level. So use my gift. Okay? So our confidence level is 92%. Go to the 92%, and then our Z alpha divided by 2 is 1.75. 75. So you don't have to calculate it again. So 1.75 sigma square. So how do you find the sigma square? Did the problem tell you anything about the sigma square? The variance? No, right? So how do you do that? You use sigma approximately equal to range divided by 4. What is a range? The range is largest value subtract the smallest value, which is 90,000 subtract 60,000 divided by 4 equals to 7,500. Okay? Then the next one, we find our standard deviation. When we plug in, just square it. How do we find the sampling error? There is a keyword for the sampling error. What is that? Within. So we want to be within 1,000. So our sampling error equals to 1,000. So then it's time for us to plug in 1.75 square it sigma 7,500 square it sampling error 1,000 square it equals to 172.3. Okay, that is our sample size, but you still have the last step to do, which is round up. Round up. Right now, our n equals to 1.72.3. But we need to, our final answer, we need to round up, which is 173. So we choose D as our answer. So So I don't think we have time for asking questions, unfortunately. Yeah, if you have just after a session, come to find me. We can do those things outside this room. So then this one. 40% of adults favored capital punishment. A sample size 150, 77 in favor. Researchers want to know if the proportion in favor has changed. Significance level 0.02. What conclusion can you make? Actually, you need to do the whole test of hypothesis to make your conclusion. What is the first step of the test of hypothesis? Find the HO and HA, right? And the relationship between HO and HA, they are always opposite with each other. The HA is the thing you want to prove. here, what do you want to prove? You want to prove the proportion in favor has changed. And what is our target parameter here? What is our target parameter here? Mu or P, which is proportion, right? We all mentioned the proportion in favor has changed, which is our target parameter is P, which is P not equal to what? P not equal to 40%, which is 0.4. HO always equal to 0.4. This is our HO and HA. Then find our test statistic. Right now, do we have the large sample size or small sample size? Actually, do you need to check that? No, because in this case, in the proportion case, we only require large sample size. Not like the mu. The mu, we have large sample situation and small sample situation. But in the proportion, we only require large sample situation. So you don't have to check whether the sample size is large or not. Then right now we are doing the test of hypothesis. Then we use this formula. Z equals to P hat minus P0 divided by P0 Q0 divided by N. What is P hat? P hat is a proportion of our sample. How do you find that? P hat is the successes. You see our success here is how many people in favor, which is 77 divided by the sample size, 150, equals to 0.51. What is P0 here? P0 actually just inside the HO and HA. It is P0 is 0.4, equals to 0.4. And then plug in P hat 0.51, subtract 0.4, divide by 0.4 times Q0. How do you find the Q0? Q0 equals to 1 minus P0 equals to 0.6. Okay, 0.6 divided by our sample size. Our sample size is 150. Then our Z value equals to 2.75. Okay? Then next step, to do our rejection region. So what is the location of our rejection region? On the two tails. Why? Because the location of the rejection region depends on the sign in the HA. The sign in the HA is not equal to. Not equal to means this is a two-tail test, which means our rejection region is on the two tails. And then what is this is our rejection region. This is our rejection region. Combine those two is our total area of the rejection region. Then next, what is the size of our rejection region? The value of alpha. In this case, the alpha equals to 0.02. The alpha is also called significance level. Here, alpha equals to 0.02. Okay? So here, this one should be alpha divided by 2 because the total area equals to alpha. Then the single area is alpha divided by 2 is 0.01. This is also alpha divided by 2 equals to 0.01. Then find the corresponding Z value. Here, this area is 0.01. What is the area here? 0.49, right? Then use this area in the Z table to find the corresponding Z value equals to 2.33. This is negative 2.33, symmetric. In order to make the conclusion to check our test statistic, whether the test statistic falls into the rejection region, the value of our test statistic is 2.75, right? 2.75, where is 2.75? Approximately 2.75, which is falls into the reject region. Then our conclusion is reject HO, okay? So reject HO, which is there is sufficient evidence to indicate HA, which is proportion in favor has changed. Proportion in favor has changed is HA. So we choose C as our answer. Yes?
Every time that our test statistic falls into our rejection region, we reject HO.
Yes.
Every time.
Okay? Then next is how to find the rejection region. And you can see our value is T. What does that mean? We probably have the small sample size. That's why we use the T value. So let's see here. Our sample had 15 cigarettes, and the mean standard deviation. If you want to support the claim, what is our claim? The average is less than 440. What is the rejection region? So what is our target parameter here? Average, which is mu, right? Then what sample size? Do we have large sample size or small sample size? Small, because we have only sample size is 15. So then that's why next, then what is HO and HA? HA is the thing you want to prove. HA, you want to support the claim. That is the thing you want to do, you want to prove. What is our claim? The average is less than 40. So mu less than 40. You want to prove this is true. And HO, mu always equals to 40. Okay? And then we don't do the test statistic because this is not required. We only do the rejection region. So since we have the sign in the HA is less than, then what is a location of our rejection region? Lower tail, upper tail, or two tails? Lower tail, because our sign in the HA is less than, we go to the left. Location of rejection region is on the lower tail. And then what is the size of our rejection region? Equals to the value of alpha. So this is our reject region, and this value, this area equals to alpha equals to 0.05. The problem tells you here. Then, right now, do you want to go back to the z table?
No.
To find the corresponding z value? No, because we have small sample size. That's why we need to use a t table. Okay, this is important to pick up a right table. So the t table, how do we do that? T, alpha, and degree of freedom. What is our alpha? T alpha is 0.05. What is our degree of freedom? Degree of freedom equals to the sample size subtract 1. Our sample size here is 15. Then our degree of freedom is 14. So using the t table here, we go to the column, which is with 0.05. This is the value of our alpha. And then go to the 14th row to find the intersection. Our z value is 1.761. T value is 1.761, but it's negative because this is below the mean, 0. The t value is negative. Okay? Then our rejection region is t less than this t value. which is t less than negative 1.761. We choose A as our answer. Good. And then next one is an interesting thing, the type 1 arrow and type 2 arrow. How do you do that? We have HO and HA, and then what is type 2 arrow? How do you do that in order to solve this kind of problem? There are two steps. The first step is to write down the definition of type 2 arrow. Then the second step, you just need to translate it to the English. No, just translate it. Okay, so what is the definition of the type 2 arrow? Type?
You reject HA when it's actually true.
Yes. So we are saying HO is true, but really HA is true. You are saying something is true, which means that is not necessarily be true. But really HA is true, which means HA is the really true, is a true thing. Here you say HOO is true, but you are wrong. Really HA is true. Okay, this is the definition of type 2 arrow. Then next step, just translate it. Translate, we are saying, what is our HO here? HO, the machine works properly. But really, what is our HA here? The machine does not work properly. Machine does not work properly. So what choice we should choose? But really, we choose A as our answer. So good. First, write down the definition. Second, translate it. Good. And then a new spray is used on 200, and then the new is used on 200. The old is used on 100. The average is 240, and the variance old. The previous one is for the new. The second one is for the old. The average and the variance. Find the 90% confidence interval for the difference in the average yields. So right now, I want to ask you how many samples we have. 2. The first one is new. The second one is old. Then, what target parameter we are dealing with, mu or p? Mu, okay? And then, do we have large sample size or small sample size? Large. Then, go to the chapter 9 stuff. Because chapter 9, what we are doing is dealing with 2 samples. So, we go to here. 2 samples. We have 2 samples. Our targeted parameter is mean, which is mu. Then, by the way, are those 2 samples dependent with each other or independent? Those 2 samples. Do they have any relationships, the old and new? No, which means they are independent. We go this way, and we have large sample size. We go this way. And then what we are doing, we want to construct the confidence interval. Then this is a formula we want to use. Okay? Excuse me. Independent. So this one is x bar 1 subtract s bar 2 plus minus
Z alpha divided by 2 root square sigma 1 square divided by n1 plus sigma 2 square divided by n2. So just plug in the value x, we use 1 as our new, okay? We use 2, we use 1 as our new, we use 2 as our old. So the average, the mean of the new is what? The average is 240. Subtract the average of the old is 227 plus minus this Z alpha divided by 2 depends on our confidence level. In this case, our confidence level is 90%. So go to the 90% here. Our Z value is 1.6445. And times, which is, this is the variance of new. The variance of new is 980 divided by the sample space of the new sample, which is 200 plus the same thing, the variance of the old, which is 820 divided by the sample space, the sample size, which is 100. Then we simplify these, we get this is equals to 7.05 to 18.95. We choose C as our answer. Okay? Once you identify what is the type of this problem, you just plug in the number. That's it. So yes.
What's the number before
240. Is that before 240 subtract 227? Okay, then use a p-value. Find the p-value and use a p-value to make a conclusion. So right now, we still, by looking this table, how many samples we have? 2 samples. The first is low fat, the second is low carb. Okay? And then the sample size tells you, the mean loss tells you, and the standard deviation tells you. The mean loss, which means because we use those 2 diet to reduce to reduce what? To reduce the weight. So we want to reduce weight. So which means the more weight reduced, the better it is, right? Then if you want to prove the lower carb diet is more effective, what is a corresponding p-value, and use it to make the conclusion. So first, what is our HO and HA here? If you want to prove the low carb diet is more effective, which means the mean of it, we use LC to represent the low carb. It subtract the mean of the low fat, we use LF to represent that, is bigger than 0. Because the mean loss by using the diet, low carb diet, is larger than the mean loss by using the low fat diet. Okay? HO is mu LC minus mu LF equals to 0, always equal. Then what is our test statistic here? We have 2 samples. Those 2 samples are independent. They don't have any relationships. So independent, 2 samples independent, and sample size is large.
so sample size is large. Our test statistic is this one. We use z equals to x bar LC subtract x bar LF subtract 0 divided by the sigma LC square divided by n LC subtract n LF sigma LF square. We plug in the number. We just write down, go through here, equals to the mean of the lower carb diet, which is 13.2. Subtract the mean of low fat diet is 4.1. Subtract 0. Divided by the variance of the lower carb diet. Remember, just be careful, because here the problem tells you the standard deviation, but here you need to square it. So remember, you need to square it. This is not a variance. If the problem tells you the variance, you just plug in the number. Don't need to square it. So just be careful. Here, it's lower carb. It's 5.2 square divided by the sample size, 60 plus 66, and 66. This is 3.5 square equals to 11.79. Okay. Then, next, find the p-value. What is the location of our p-value? Upper tail, lower tail, or two tail? Depends on what? The same as the reject region. Depends on the sign in the HA. What is in our HA here? Greater than. So we should go to the right, which means the location of the p-value is on the upper tail. And then, what is the bound of our p-value? The bound of the p-value is our test statistic. Our test statistic is z equals to 11.79. So this one is our test statistic, equals to 11.79. This shaded area is our p-value. Okay? Then, if you say your test statistic z equals to 11.79, do you need to go to the z table to find this area? No, because this z value is super large. Then the area, this shaded area, which is the value of p-value, is approximately 0. Okay? Then our p-value is approximately 0. How do we make the conclusion? By using the p-value. Comparing the p-value with what? Alpha. With alpha. Since our p-value is less than alpha, then we reject HO and conclude that there is sufficient evidence to show HA. In this problem, is a low-carb diet is more effective. Good? If you want to prove HA is right, then there is sufficient evidence to show HA. If you want to show the HA is not right, then there is insufficient evidence to show HA.
So for this one, since we rejected,
Yeah, we choose D as our answer because p-value is less than alpha, then we reject HO. Then we think HA is right? So there is sufficient evidence to indicate HA. Then we are close to the end. 36. Oh. So I don't think we have enough time to finish all those problems. So we can choose one of them to do. How about we do this one first? So just let's make the quick conclusion about the chapter 9, because rest of the problem is about the chapter 9. So the chapter 9 is here. What we already did, 2 samples for the mean, and the relationship between those 2 samples are independent. So we did a large sample, and if we want to do the test of hypothesis, we use this formula as our test statistic. And if we want to build the confidence interval, we use this formula. Okay? Then the small sample size, if this is a small sample size, we should use t. And there is a common variance, SP squared. Common variance, another important thing is degree of freedom, which is use a sample size 1 plus sample size 2 subtract 2. Because you need to use a degree of freedom to find the t value in the t table. And also this is formula for the confidence interval when our sample size is small. Another thing I think is the special thing in the chapter 9 is that the dependent samples, which means in this case, we only require the small sample size. And then we use a t value as our test statistic. Pay attention to that. This one, the d means the difference. ND means the size of the difference, sample size of the difference, which means how many difference we have. And only subtract 1. And also building the confidence interval, we use this formula. Just at the very end, we have 2 proportions. There is only independent samples are required. Only large sample size are required. That's why we only have the single line, single column here. And then do the test of hypothesis. Use this formula. Remember, this is a p-hat. How to calculate the p-hat? Use the successes in both samples divided by the sum of the sample size of those 2 samples, n1 plus n2. And this is the formula for building confidence interval. And I'm sorry we didn't finish all those things. So we still have 1, 2, 3, 4, 5 problems. And if you have any questions, I will wait outside. You can come to find me. Just good luck on your final.